Hi students, in this class we shall be taking continuity and differentiability. This is chapter 5 for class 12 NCERT mathematics. Okay, so let us begin with the topics. So what is continuity? Continuity, we know that it is by the word itself we mean that it is without any break or gap. Say for example, axis is like this and the x-axis is like this, and the function is continuous. Okay, say from point A to point B, say from here to here, if you can draw the graph, if you can move along the graph without lifting your pen, in that case we can say that the function is continuous. There is no break in the curve. All points are connected throughout. Okay, such a graph is called a continuous curve. Okay, such a curve is called a continuous curve or a continuous graph. Okay, so if the graph of a function has no break or gap or jump, then it is said to be a continuous function. A function which is not continuous is called a discontinuous function. Say for example, this is the y-axis, this is the x-axis, and if there is graph like this, say for example, for some values it is defined like this, and then for some values it will be something like this. Okay, so at this point it is not defined here, but it is defined here. So suddenly if it is moving from this point to this point, if it is moving from A to B, it cannot go till B, without jumping this point. Okay, so the graph breaks at some point. So if there is a break occurring in the graph, then we say that the graph is not continuous or the function is not continuous. So this is a not continuous function, this is a continuous function. Okay, so now let us see some examples of continuous function. Okay, so the first example is the identity function. This is the identity function. Which maps every real number to itself. Okay, so if you take x equal to 1, you get y equal to 1. So the graph point will be here. So this is 1, 1. So in case if you take x equal to 2, you get y also equal to 2. Y means f of x. Y is equal to f of x. So that's why again what you get here is this point. So like that we can get infinite many points, and this line represents the graph of this curve. Okay, so therefore this line is a continuous function. Okay, this line is a continuous function. Okay, now we shall move on to the next example of continuous function. Look at the curve of sine. Sine curve is going again like this. It is a continuous curve. Okay, on all real numbers, throughout the real numbers it is defined and it is continuous. Okay, next example would be of cos x. Here also the function is continuous. The graph is continuous without any break. Okay, next is the graph of modulus of x. Modulus of x, the curve is like this. See, when you put x equal to minus 1, modulus of minus 1 is equal to plus 1, positive 1. So it is coming here. Same way, if you take modulus of plus 1, it is coming here. Okay, again it is plus 1. So you get the point. If modulus of 0 is 0, so the graph will be like this, straight line on the left hand side and straight line on the right hand side, and still you can draw the graph without lifting the pen. So such a graph is called a continuous graph or continuous curve. Okay, now we shall move on to some examples for discontinuous function. Let us look at this graph. This is the graph of the greatest integer less than or equal to x. Okay, this is greatest integer less than or equal to x. Now let us analyze this graph. What is greatest integer? Greatest integer less than or equal to x. Now let us look at this graph. So when x is 0.1, the graph, the y will be 0. When x is 0.2, the y will be 0. When x is 0.3, y will be 0, because 0 is the integer which is less than or equal to those points. Say for example, f of 0.2. What is f of 0.2? It will be 0. integer, okay, greatest integer which is less than 0.2. F of 0.5, that will be again 0. F of 0.7 will be 0. What will be f of 1? F of 1 will be equal to, as soon as it reaches 1, f of 1 becomes the integer itself, because it is an integer which is less than or equal to 1. So if it becomes 1, then again, so it jumps to this point. So now f of 1.5, f of 1.5 is 1. F of 1.8, that will again be equal to 1. Now what is f of 2? What is f of 2? As it comes here, when x equal to 2, the graph is defined here, not here. See, the open circles represent that the points are not here. The dark circles represent that the points are here. The value of the function is coming here. Okay, so f of 2 is 2. So that is what we observe is that as whenever we reach an integer, the graph jumps up. Okay, there is a break in the graph and suddenly the values come here. So this is also called a step function. Step function. Okay, the graph of this function looks like a step, so it is also called a step function. So it increases in steps. Now let us look at another example of tan x. We know what is tan x. Tan x is a trigonometric function. So here the graph of tan x is like this. Okay, tan 0 is 0 and then tan 90 is undefined. So this is the point. This is the point where it is pi by 2. Okay, this is the point where it is pi by 2 and this is like that. Okay, so it's the point where it is pi by 2, the tan function is not defined. Means it goes to positive infinity or negative infinity at different multiples of pi by 2. Okay, next function is sec x. Again, here also you cannot draw these graphs using a pen without lifting the pen. Okay, so such graphs are discontinuous graphs. Okay, now we shall understand the definition of continuity of a function at a point. When can we say that a function is continuous at a point? Okay, say consider this theoretical portion. Okay, so a real function f, a real valued function f is said to be continuous at a point x equal to c. At a point x equal to c, say for example, that this is the x-axis, and there is a graph of the function like this. Okay, so now if I am talking about whether the graph is continuous at this point or not, we are talking about point wise continuity, whether the graph is continuous at this point c or not. Okay, so that is what we are trying to understand. So at this point, first thing is that the graph should, this point c should lie in the domain of the graph. That is, the function should be defined at this point. There should be a value of the function at this point. That is the first point. F of c should exist. Okay, say for example, if there is a y-axis here, f of c will be this point. F of c, this is f of c. Okay, so you get c comma f of c at this point. Okay, now what happens? The second condition is that the limit of the function should exist at this point. What do we mean by the limit of function exists at this point? It means that the function should be defined, the left limit of the function should be defined and the right limit of the function should also be defined, and both of them should be equal. The left, when x approaches c, from the left, that is called c minus. Okay, minus means from the left. When x approaches c from the left, the limit should exist, and when x is approaching from the right side, that is positive side, then also the function should be, or the limit of the function should exist. Okay, and both of them should be equal. The limit of the function when the function approaches c from the left, and the limit of the function, this is the left limit and this is the right limit, both of them should be equal. Okay, the third point is that the limit of the function at x equal to c should be equal to the value of limit of the function as x tends to c should be equal to the value of c. That is, first we said that the function should be defined at c, f of c should exist. Second was that the limit of the function exists. By definition of limit, we say that the limit exists if both the left hand limit and the right hand limit exists. And then the third point is that this limit, the value of this limit, that is the left hand limit equal to right hand limit, and both of them should be equal to the value of the function at x equal to c. Then such a function is called a continuous function. Okay, a function is said to be continuous everywhere on the real number line if it is continuous at each point of the real number line. Okay, a function is said to be everywhere continuous if it is continuous at each point on the entire real number line. The examples are the polynomial function, the sine function, the cos function, a constant function. X raised to n is continuous throughout R. You keep on putting different values of x, and x raised to n will be different for a fixed value of n. Same way, modulus of x minus a is again an example. Now, what is continuity from the left and what is continuity from the right? We discussed. We will define what is left continuity and right continuity. A function may be left continuous but not right continuous. Okay, let us see what is continuity from the left and right. That is, a function f of x is said to be left continuous at x equal to c if, as x approaches c, this is y axis, this is x axis, this is the curve of, and this is point c. So as x approaches c from the left, the limit of f of x, should be equal to f of c, okay, and the function is said to be right continuous at x equal to c if as limit x tends to c from the right side, f of x will be equal to f of c. Okay, if it is approaching from the right hand side, then also the limit of that function from the right should be equal to f of c. Okay, so if a function is both left continuous and right continuous, and both of them, then we say that the function is continuous at x equal to c. A function is said to be continuous at x equal to c if it is both left continuous as well as right continuous at x equal to c. Okay. Now let us look at some example and understand this theory, because the theory may be confusing, but now we will discuss the problems. Okay, let us look at the first example. Okay, what is there? We have the function given. We have to check whether the function is continuous. This function is continuous at x equal to 1 or not. We have to check whether the function is continuous at x equal to 1 or not. First, we will check, as there are 3 points to check. First, that f of c is defined, c is equal to 1. Okay, c is equal to 1 here. Okay, x equal to 1 means we will take that point x as c. So c is equal to 1. Okay, we will check whether f of c is equal to f of c exists or not, and what is the value. We will find out the value of f of 1. Okay, so that is f of 1 is equal to 5 here, because when we put x equal to 5, what is f of 1? F of 1 is equal to 2 into 1 plus 3, and that is equal to 5. Okay, so f of 1 is equal to 5. Now, to find the limit of the function, we need to find the limit of the function also at x equal to 1. So first we will go for the limit. Here the function doesn't have any break, so the left definition of the function and the right definition of the function at x equal to 1 will be the same. Okay, so we need not partition for the left hand limit and the right hand limit. In such cases, when the function is not broken into different pieces, we need not partition into left hand limit and right hand limit types. So we will take limit x tends to 1 f of x, that will be equal to limit of x tends to 1, the same function f of x was equal to 2x plus 3 as given. Then we will just put these values into x. We will just put these values into x and find the limit. Okay, that is 2 into x equal to 1. So x equal to 1. So 2 into 1 plus 3, that is equal to 5. Okay, that is limit extends to 1, f of x is equal to 5. Okay, and that was equal to this value. See, f of 1 will be equal to this value. So that is why we can say that f is continuous at x equal to 1. Now we shall look at the second example. Okay, look at the second example. The function given here is f of x equal to x square, and we have to show that whether the function is continuous at x equal to 0 or not. From the graph, it is clear that x square means it represents a parabola passing through 0. Okay, and here it appears to be continuous function. Okay, so here again the function is not broken, so therefore we will not break it into left hand limit and right hand limit, and at x equal to 0 we will try to find out the value of the function. Okay, when x equal to 0, f of x equal to, when put x equal to 0, okay, put x equal to 0 here. So f of 0 equal to 0 square, that is equal to 0. So we get f of 0 is 0. So yes, the function is defined in this at point x equal to 0. Second, to find the limit at x equal to 0, we will consider limit x tends to 0, f of x. We will consider limit x tends to 0, f of x, which is equal to limit x tends to 0. What is f of x? F of x is x square. F of x is x square. And now it is very simple. We just put the value of x of the limit instead of x. Okay, the limiting value of x to the value of x, and we get 0 square, that is equal to 0. And we observe that this limiting value is equal to the value of the function at x equal to 0. So we say that limit x tends to 0, f of x is equal to f of 0 also. So therefore the function is continuous at x equal to 0. Now we shall do example 3. In example 3, look at example 3. Here what we have is the modulus function. Modulus function is broken. Modulus function appears to be broken. This is the actual definition of modulus function. What is this? This is the actual definition of modulus function. Okay, so when x is positive, what happens? When x is positive, f of x is equal to x, and when x is negative, f of x is equal to minus of x. When x is negative, we define modulus of x as minus x, right? If we take minus of 2, then modulus of minus 2 will be equal to minus of minus 2, that is equal to 2. So it makes it positive. When x is negative, negative of negative becomes positive. So the definition is f of x equal to minus x when x is negative and plus x when x is positive or 0. Okay, so now let us see whether the function is defined at x equal to 0 or not. We have to check it at x equal to c is equal to 0. Okay, so when we put x equal to 0, this is the definition, this is the part which comes into play. Okay, this is where we need to find out f of 0. F of 0 is equal to f of, what is the function? What is the function? At 0, the function is defined as x. When x equal to 0, f of x is equal to x. Okay, f of x equal to x, and that is equal to 0. F of 0 is equal to 0, clearly. Okay, now the function is defined at x equal to 0, it is equal to 0, fine. Now we shall try to find out the limit at x equal to 0. Here clearly the function is broken into two parts, when x is negative and when x is positive. When x is negative and when x is positive. Okay, and in between we have 0. So when x approaches 0 from the left, we will find a limit x tends to 0 minus f of x. That is, when limit of x tends to 0 from the left, f of x is equal to, means when x is tending to 0 from the left means x is less than 0. Okay, that is, limit x tends to 0 from the left, x is less than 0, because x is lying to the left of the 0 and x is coming from the left hand side. Left hand side is always less than. Okay, so therefore the definition here is when x is less than 0, f of x is equal to minus of x. So instead of f of x, I will put minus of x. Okay, and then finally we will just put the value of x as 0. So finally minus of 0 is 0. So left hand limit x tends to 0, limit of x tends to 0 minus f of x is equal to 0. Same way, limit x tends to 0 from the right, that is x is greater than 0. Okay, f of x will be equal to limit x tends to 0. Here x is greater than 0. When x is greater than 0, what happens? When x is greater than 0, it is this definition, that is x, f of x is equal to x. So therefore f of x is replaced by the value of the function, that is x. Okay, now you just put the value x equal to 0 and finally you get 0. Okay, so limit x tends to 0 from the right, f of x equal to 0, also f of 0 is equal to 0, also f of 0 is equal to 0. So from the definition of continuity, f of 0 is defined, left hand limit is equal to 0, and means if it is left continuous, it is right continuous. So therefore f is continuous at x equal to 0. We can draw the graph continuously even when passing through 0. Okay, it forms a corner, but still we can draw the graph without lifting the pen. Okay, so therefore f is continuous at x equal to 0. Now example 4. Show that the function f given by f of x equal to x raised to 3 plus 3 when x is not equal to 0, and it is defined as 1 when x equal to 0. Now let us check whether f of 0 exists or not. F of 0, we need to check or show that the function is not continuous at x equal to 0. F of 0 is equal to f of 0 means here x equal to 0, so function is defined as 1. So it is defined at x equal to 0. Next, we need to find out the left continuity. Okay, or here the left continuity part, the left and right functions are defined in the same way. The left and right functions are defined in the same way, x raised to 3 plus 3. So we need not break them into two parts. So limit x tends to 0, f of x will be equal to limit x tends to 0 from both from the left and right. It is the same thing. F of x will be written as x raised to 3 plus 3, right? When x is tending to 0 means either x is less than 0 or x is greater than 0. Okay, either x is less than 0 or greater than 0. That is, x will just now put x equal to 0 in this case. We will put x equal to 0. What is there? 0 raised to 3 plus 3, which is equal to 3. Okay, so that is 3, but this is not equal to this. Limit x tends to 0, f of x is not equal to f of 0. So therefore f is not continuous at x equal to 0. Okay, we have verified that f is not continuous at x equal to 0. Okay, next example is example number 5. We need to check the points where the constant function f of x equal to k is continuous or not. Now we know that f of x is defined for all real numbers. F of x is defined for all real numbers. F of x is equal to k. Okay, now what is f of c? So let c be any real number. Okay, real number. So therefore what is f of c? F of c will be equal to k, because it is always k. Okay, f of c is equal to k. So this is the first part. Next part is the left hand limit as well as the right hand limit. Both the function is always defined in the same way. So limit, to find the limit, okay, to find the limit x tends to c f of x. Okay, what is that? Here limit x tends to c f of x is limit x tends to c. See, f of x is always defined as k, and here it is independent of c. Therefore again this is k. So this is 2. So therefore limit x tends to c f of x is equal to f of c. So therefore this implies f is continuous for all c, right? C was any real number. For any real number we have shown that continuous for all real numbers, continuous for all real numbers. Okay, next question. Question number 6. Prove that the identity function on the real numbers given by f of x equal to x is continuous at every real number. Okay, again it is the same type. So f of x will be equal to x, right? F of x is equal to x, the identity function. So first let c be any point, any real number. Let c be any real number. Now what is f of c? F of c will be equal to, what is f of c? F of c will be equal to c, because instead of x we are putting c, then we get c. So f of c is equal to c. This is the first part. We found the value of found the value of f of x at x equal to c. Next what we do? We find the limit x tends to c, f of c. What is that? That is limit x tends to c x, because limit x tends to c f of x will be equal to, f of x is defined as x, identity function. Okay, so this we just put, instead of x we will put the value of x, that is c. So we get c. So we get, this is 2. So from 1 and 2 what we have is limit x tends to c f of x is equal to c. So therefore f is continuous for all real numbers. Okay. Next question number 7. Is the definition of the function, or is the function defined by f of x equal to modulus function a continuous function? We need to check whether it is a continuous function or not. We have seen the graph of the modulus function. Okay, continuous function means it should be continuous everywhere on the real number line. It should be continuous on everywhere on the number line. So let us first of all define what is f of x. F of x is equal to modulus of x. Modulus of x means, what is modulus of x? Modulus of x is partitioned value. So it is equal to x when x is greater than 0. It is equal to 0 when x is equal to 0, and it is equal to minus of x when x is less than 0, right? This defined like this. Now what is, let me take any value, which is less than 0, right? Let c be a negative number. Let c be a negative number. Okay, let c be a negative number. So then what happens to f of c? We check for both left side and right side. Okay, so here what is f of c? What is f of c? F of c will be, since f is a negative, c is a negative number, f of c will be equal to minus of c, right? F of c will be equal to minus of c, because minus of c remains positive since c is negative. This is your first part. Now limit x tends to c f of x for negative number. C is negative number, right? C is less than 0. C is less than 0 is given to us. So when for a negative numbers, f of x is defined as minus of x, right? X tends to c minus of x. What is that? When you put x equal to c, you get minus c. Okay, so therefore here limit x tends to c f of x is equal to f of c, right? For the left hand side of the of 0, for the left hand side of 0. Now f of 0, what is f of 0? F of 0 is equal to 0. The function is defined. Okay, from the left also it is 0 and from the right also it is 0. We have shown that in example number 3. In example number 3 we have shown that the function is continuous at x equal to 0. So we will continue for the right hand side. Okay, so let c be positive. For positive numbers, whether it is continuous or not, it is continuous for x equal to 0. It is continuous for x equal to 0. This is continuous for x equal to 0. Okay, now it is continuous at x less than 0 also. Now whether it is continuous at x greater than 0 or not is what we are going to check. So let us see f of c. F of c is equal to c, because at positive points it is defined as positive value of c. So right, so limit x tends to c, where c is positive. Okay, f of x is defined as limit x tends to c, the positive value of f of x, that is x. F of x is defined as x when x is positive. Okay, when x is positive, and that will be equal to c. Okay, when you put x equal to c, you get c here. So therefore what happens is limit x tends to c, f of x equal to f of c for right side also and for the left side of 0 also, and it is continuous at, so it is continuous for all negative numbers. F is continuous for all negative numbers. F is continuous for all positive numbers, and f is also continuous at 0. F is continuous at 0. So therefore f is continuous at all real numbers, for any real numbers, that is f is a continuous function. Yes, it is a continuous function. Now let us look at example 8. For example 8, let us discuss the continuity of the function f given by f of x equal to x raised to 3 plus x square minus 1. Okay, so here f of x, what is f of x? X raised to 3 plus x square minus 1. First we will check for, let x be any value, let c be any value. Okay, let c be any real number. Okay, now what happens when c is less than? Let us approach, what is the value of f of x at c? What is the value of f of c? What is f of c? F of c is equal to c raised to 3 plus x, plus c raised to 2 minus 1. Okay, this is the value of f of c. Now let us check limit x tends to c for f of x. Okay, that is equal to limit x tends to c. What is f of x? F of x is x raised to 3 plus x square minus 1. We just need to put x equal to c here. So we get c cube plus c square minus 1. So we can see that this is the f of c and this is the limiting function, and the second part. So therefore f of x, limit x tends to c, f of x is equal to f of c for all c belongs to R. Okay, therefore f is continuous at x equal to c. X equal to, for all x, f is continuous for all real numbers. Okay, next question. This is again the same way. Here f of x is equal to 1 by x and x is not equal to 0. It is defined like this. Now we need to check whether this function is continuous or not. Okay, let us check this function. Now let us take, let c be any real number. Okay, now what happens to f of c? F of c will be equal to 1 by c. Clearly c is not equal to 0. C is not equal to 0 because c cannot be taken as 0. The function, the c, that point 0 does not belong to the domain of f. Okay, now f of c is equal to 1 by c. Next what we are doing is finding limit x tends to c, f of x. Okay, that is equal to limit x tends to c 1 by x, and that is equal to, again look here, that will be equal to 1 by c. So this is the first point, this is the second point. So we can say that from 1 and 2, limit x tends to c, f of x is equal to f of c. Okay, so therefore f is continuous at x equal to at for all real numbers, for f is continuous for its domain, f is continuous in its domain, f is continuous for all real numbers not equal to 0. At x equal to 0, the function is not defined and it is not there in the domain of f also. So we need not worry about being not continuous or not. Okay, so this function is continuous for all real numbers not equal to 0. But at x equal to 0, the function is not continuous because the function itself is not defined there.